I think I missed what you said about layer normalization and how that relates to no free lunch. Could you just repeat that point?
Yeah, sure. What do I mean when I say there is no free lunch? In the best case scenario, you want to have invariances everywhere in front of at least one of these guys, in front of batch norm, weight norm, or layer norm. When it comes to weight matrix rescaling, it's a good property that if you change your weight, if you multiply it by alpha, then alpha is going to end up going away. If you scale it up or scale it down, it ends up going away. Why is it a good thing? Because then you are going to be less sensitive to your initialization scheme. And all three of them have that. When it comes to weight matrix recentering, if you take W and subtract a constant from it, then it's a good thing that it is invariant to those subtractions or shifts. Again, for the same reason. You don't want to, when you are initializing your weights, you can just initialize them to have actually normal distribution with mean 0 and some standard deviation. And if you don't have this invariance, then you have to be very careful. Should I sample from a normal distribution with a particular mean or some other mean, or mean being 0 when you're initializing your weight matrices? Same thing for weight vector rescaling. This doesn't have it. Layer norm doesn't have this property. The other two have it. Weight norm definitely has it. And the way that weight norm works is you take the norm of one of these rows of your matrix. So you take the norm of that, and then you divide that vector by the norm. So your vectors are always going to have a norm of 1. Layer norm doesn't have it because you are not doing your operations on the weights. You are doing them on the dimensions of your hidden units. These are really important. Data rescaling, one of the reasons that we subtract the mean and divide by the standard deviation of our data is because neural networks usually don't like data that have different scales. Maybe one of the variables in your when you do your feature engineering, if one of the features has a scale from negative 10 to the power 3 to 10 to the power 3, it's a small scale, and then suddenly one other variable has a scale from 10 to the power 5 to negative 10 to the power 5. And then under no circumstance, your neural network is going to converge. Same thing for the mean. If you take your data, shift it to the right, you want to have a model that is invariant to those shifts. You can rescale your data, you can recenter your data, but it would be good if you don't have to do those steps. So these invariances are useful. Layer norm has data rescaling, it doesn't have data recentering. So if you shift your data to the right, then your model is not going to converge. This is also important. Single training case. If you take one of your training cases and scale it, perhaps this is a bad property to have. And layer norm has that property, is invariant to that. Perhaps this one is not a good one to have because of the outliers. Maybe layer norm is going to miss those outliers. Or maybe it's a good thing because it's going to end up being less sensitive to them. But as you can see, there is no free lunch. Some of them have invariances, some of them don't, and they are appearing in different locations. Does that answer your question?
Yes, it does. Thank you.
Yeah, sure.
Professor, can you again tell what exactly data recentering means?
Data recentering is, let's say you have an image and then you shift it to the right, add a scalar value to it.
Okay.
Now your data is not centered around 0 anymore. It is centered around 500. It's a number that you chose.
Okay, I see. But then why won't layer normalization be invariant to that? I mean, that can also learn like that the offset that's there, won't it?
No. So the offsets that layer norm is learning, they have nothing to do with the mean of your data.
I see.
They have to do with the mean of the dimensions in your data. Yep. So you're taking the mean across the channel, not across the data.
I see. Okay. So if we consider any vision tasks, again, I mean, I'm more used to vision tasks. That's so. But then we are used to doing like normal, like before passing on to the images, passing on to the like the images to the model. We always normalize it, right? So invariance to data recentering will not be needed in that case, right?
We have to be careful. When you are talking about the image itself, you are talking about the 0th layer of your neural network.
Yeah.
But what happens when you are 10 layers deep in your neural network, and then suddenly those hidden units are shifted to some other center? And this is actually what is called internal covariate shift. And why does that happen? The first layer doesn't have any weights, the 0th layer. But the layers after it are going to depend on some weights. And throughout the learning, you're adjusting those weights. It means that the statistics of your hidden units could end up being messed up. They could have messed up mean and variances. Batch norm is going to take care of that. Per each layer, you're going to take care of that. Weight norm and layer norm don't do that.
I see. So in terms of applications and like the just sheer performance, or maybe in terms of like generalizability, how this will actually affect, I mean, is so, like theoretically it's invariant, right? But then like from a pragmatic point of view, is there like, do you know any of papers which say like this is a very important issue and this needs to be tackled or something like that?
Yeah, so let me show you a paper. These are all the things that we cover in part 1 of the course. And this is a good paper to read. And it is discussing why not batch norm and how can you actually get rid of it when it comes to images. And this is giving you one of the best performances in terms of ImageNet top-bound accuracy.
Oh, I see. So they don't use normalizations at all.
No, they don't.
Oh, okay, that's interesting. So,
But then at
so
the
what?
same
Yeah,
time, there is some weight normalization.
yeah.
It's actually weight standardization going on
Okay.
in that other paper. So there is a still normalization going on.
I see. So, so one of the other thing that you mentioned is like if you, I mean, so when we compare any like see any spatial temporal data or like video related tasks, right? Many of them use batch normalization because it makes it much more efficient, right? So, do you know if, I mean, if do you know any other workarounds of efficiency I mean, in terms of normalization that could be done if you don't want to do batch normalization in that case?
So yes, there are all sorts of normalizations like batch norm, weight norm, layer norm, group norm. I know for videos, people do group norm.
Okay.
And then there is instance normalization. All of these normalizations are important.
Yeah.
And each one of them have their own applications. For instance, instance normalization, you can use it to generate images in the style of another image. So they are good for stylization.
I see.
We are going to see that. We are going to see all of them.
Okay. Yeah. Thanks for this. Yeah. Thanks a lot.
Have a good one.
Yeah. Bye.
So when you're going over how weights impact the centering of the data, like several layers deep, was that for the data set recentering or was that for the weight matrix recentering?
It's for both of them.
Okay.
This is going to be invariant to data recentering, batch norm, but then it's also going to be invariant to recentering the hidden units.
And
because think of it, from one layer of your deep neural network to the next one, you are just transforming your data. You still have your data set in another coordinate system.
right. Okay. And then because it's being transformed over many layers, you can cause it to shift or recenter.
Yeah, exactly.
Okay.
So it could happen that your original images or your text is centered, but as you go through layers and keep transforming your data, then they might end up not being centered at all. And if they are not centered, then there is going to be a nonlinearity on top of them. And then most of these nonlinearities have a saturation. Even ReLU has a saturation. If you go below 0, you're killing those. It means that there is not going to be any gradient over your parameters, and then there is not going to be any learning.
So you're pushing the data out of the range where you can actually apply a nonlinearity to it.
Exactly.
And is that, so is the recentering then, are you basically trying to keep the data within its original distribution or within the distribution that works for, okay, that all makes sense now.
You want to keep it around 0, and then you want to keep them around normally distributed as much as possible.
So does that mean when the data comes in, it's normally distributed?
No, it's not. And it's not going to be. When I was saying that, I was considering the first two statistics of your data, which is the mean and the variance of your data. But then still your data could be skewed. It could have a fat tail. So you
Okay.
can take a look at the higher order moments of your data.
So you just want, okay, mean and variance. That makes sense.
So you want the mean and the variance to be reasonable. The mean to be around 0, the variance to be around 1.
So then that's the data set, but what about the matrix itself? I guess you're learning.
So one thing is, if, for instance, if you do weight normalization, and if your original data is already centered, then after multiplying by a weight that is going to sum to 1, it has a norm 1, your variance is going to end up being reasonable. It's going to end up being around 1 again. So that's why weight normalization is working relatively good.
Okay. I think that all makes sense.
Perfect.